Hi all. Today we will study another very ingenious method called the transportation method for deriving concentration of measure inequalities. So this class will be about an introduction or a high level idea about what this method allows you to do, and we will start digging into it by presenting presenting the idea of coupling and optimal transportation, which are important ideas in probability and optimization in their own right. So let's start with a high level introduction of the transportation method for proving concentration inequalities. So recall that suppose we want to show concentration of measure for some random variable z having probability distribution p. As always, we know that if we control the log moment generating function of z, then we can hope to control the tail of z using the Chernoff bound. So in particular, quadratic log moment generating functions give sub-Gaussian tail bounds and so on and so forth. So against this backdrop, what have we studied so far? We've looked at the well-known entropy method, which essentially says one can control the moment generating function log expected value of e raised to lambda z for some real number lambda by basically controlling the entropy of a certain random variable, in particular ent of e raised to lambda z, and then by using or appealing to an integral formula for the log moment generating function, which is of the form log expected value of e raised to lambda z expressed as an integral from 0 to lambda of the relative entropy or KL divergence between two measures q subscript t and the original measure p of z divided by t square dt, where if you recall, q of t was defined using the transformation or the Radon-Nikodym derivative dqt by dp being defined as e raised to tz divided by the expected value under p of e raised to tz. So the entropy method crucially relied on this kind of integral equality and further bounds on the entropy of e raised to lambda z, which can be translated on a bound on this integrand to in turn control the log moment generating function in the sense of an upper bound. Now what the transportation method does is somewhat related in spirit, but the exact tools are quite different and very elegant. It also seeks to control the log moment generating function, okay, which if to be more precise, it's the expectation according to z distributed according to p of e raised to lambda z using the variational formula for log moment generating function that we have seen earlier. Which is of the following form. So log expected value under p of e raised to, let's say, the centered version of z, z minus its own expectation, is the solution to an optimization problem over all measures or probability distributions q absolutely continuous with respect to the original distribution p of z of the expected value under q of z minus the expected value of p under z minus the divergence between the measures q and p. So we have seen this variational formula, we have derived this variational formula in a previous lecture, and this is exactly what the transportation method is going to appeal to. Okay, so this is something that we saw earlier. Now with this formula in hand, suppose we can somehow show, so if we can show somehow that there is some number v which is positive such that for all absolutely continuous measures q with respect to p, this quantity here, the eqz minus epz, can be bounded in terms of dqp itself as, let's say, eqz minus epz is bounded by square root of 2v dqp. Okay, all that's important here is the square root dependence on dqp. And let's call this inequality, let's label this inequality as star. Then what we will have is an upper bound on this difference of expectations with respect to q and p for z, and we can go ahead with upper bounding the right hand side, the objective function in the variational formula as follows. So log ep e raised to lambda z minus epz, okay, is at most the supremum over all absolutely continuous q of lambda times. So recall that we have a lambda multiplying z, so you can so this eqz minus epz now gets a lambda multiplier, and if star is true, then we can substitute the upper bound for eqz minus epz, and then finally subtract dqp. Okay. Now we can think of dqp as a variable in this optimization problem, as any number, any non-negative number, in fact any real number, and we can find a further upper bound here by just saying supremum over all numbers mu of lambda square root 2v mu minus mu. Okay, because dqp is some number which is non-negative, so we are just allowing dqp, we are replacing dqp by mu and allowing mu to take any real valued number. And if you solve this explicitly, this you can just treat as a quadratic function of square root mu, and the answer to this is in closed form lambda square v by 2. Okay. So what we have shown is that if there are bounds of the form star where a difference of expectations of the same random variable with respect to two different measures is upper bounded by a function of the relative entropy or KL divergence, then you can look forward to actually showing bounds on the log moment generating function, in particular of the sub-Gaussian type. So this means that, so this implies sub-Gaussian concentration as an example. Of the tail of Z. So inequalities of the type star are precisely what are called transportation cost inequalities. So inequalities like star are called transportation inequalities for reasons that we will come to soon. Or transportation cost inequalities, and can often be shown and can often be derived or shown using ideas from what is called coupling of probability distributions. Of probability measures or probability distributions. Okay, so for now, at a high level, for a high level overview of the transportation method, it suffices to say that the transportation method is focused, all the action in the transportation method is focused along proving inequalities of the following type. where a difference of expectations with respect to the same random variable with respect to different measures can somehow be suitably upper bounded by uh, in this case functions of the KL divergence between these measures, and that is accomplished in turn using ideas from what is called optimal transportation theory and coupling theory from probability. So, what are transportation cost inequalities and what is the relationship to coupling? So, for this let us take a detour to what is called Monge's optimal transport problem. So, this is a very old problem in actual transportation of materials and operations research that Monge actually formulated back in the 1700s, many centuries ago. So, to illustrate this optimal transport problem, let us consider the example of the motivating example of transporting let us say iron ore that has been dug up from mines, from various mines or sites, and how to transport it to processing sites or factories. So, imagine that there are m sites 1 through m at which let us say some material is dug up or iron ore has been dug up and heaped up, and essentially the number of units of iron ore available at each site I is Pi. So, P1 through Pm are the amounts of iron ore that are being generated or being dug up. Let us normalize things such that the summation of all these Pi's is equal to 1. Okay, so there is a total of 1 unit of ore that has been mined. On the other hand, you have a bunch of n processing sites or factories, each of which can process or mine or turn the iron ore into finished products at capacity Qj. Okay, so the capacity of the site J is Qj. So, in some sense, the demand from site Qj for iron ore is Qj, and since there is only a total of 1 unit totally being mined, let us also assume that the total amount of processing demand that is required for iron ore is equal to 1. Okay, so there are m numbers that sum to 1, m non-negative numbers summing to 1, 1 for each site on the top, and there are n numbers, non-negative numbers that are also summing to 1, representing the demands. Okay, so the problem here is to essentially find a plan or a way to move iron ore from each site 1 through m to each site 1 through n, if required by splitting the amounts at each site. So, we have to come up with an allocation which is denoted by Pij. So, Pij is the fraction of traffic or iron ore that travels on the path I to j and reaches let us say from any I to any j, or you can even think of the problem in reverse. There is no directionality here, it can even be going from j to I. Okay, depends on your point of view. So, Pij is the amount of traffic out of the total Pi that goes along the path I to j, and naturally in order to satisfy the exact demands at the receiving end, which is the green end, as well as the conservation of mass at the sending end, we require the following constraints to hold, equality constraints. So, for every source site I, the total amount of material leaving that site, which is the sum of Pij over all j, must equal Pi, and likewise the total amount of material entering each destination site, which is the summation over all I of Pij, must be equal to the total demand, must satisfy the total demand Qj at that site. So essentially this is a condition on Pij that says if you sum along, if Pij were a matrix of Ij's, the row sums and the column sums have been prescribed. Okay, all that is left is for someone to design the exact numbers Pij for every I and j. The Pij is often called a routing plan or a transference plan. Okay, and how can we design different transference plans? Suppose we assume that there is a cost Cij to transporting material along the path Ij. So, this could basically perhaps be determined by the distances of j and I, if they are all lying together in some space. It could depend on the route length and so on. But imagine that there is some Cij given, that is a non-negative number, which is a cost per unit of using the path I to j, ij. So every piece of material that travels along, if a unit amount of material travels along the path ij, then the cost of making it travel along the path ij is going to be Cij. So this implies that if we have a routing plan Pij, which of course satisfies the marginal constraints at both ends, the sum over all j and the sum over all I, then the total cost that this routing plan gives with respect to the given costs C and the given source and target distributions P and Q is just obtained by summing over all I and all j of Cij Pij. So this is the total cost of the routing plan. Okay. And one is essentially in the optimal transportation cost problem interested in finding the allocation or transference plan Pij to minimize the total cost as best as possible. So the optimal transportation cost problem says that for fixed P and Q, fixed distributions P and Q on the I and j terminals and a given cost structure Cij for every I and j. The question is how to achieve the minimum possible cost CPQ denoted by CPQ achievable by careful design of the Pij. Okay, so the optimal transportation cost problem is all about how one tries to design the Pijs to actually minimize the total transport cost. So this leads one to formulate the following optimization problem, which is defined by this number CPQ. So CPQ is basically the least possible total transportation cost of moving all the material from the I terminals to the j terminals, while satisfying on one hand two types of constraints, which are essentially kind of constraints about the marginal. So if you can imagine Pij as a distribution on you can imagine Pij as a distribution on edges ij. Okay, so Pij is a probability in some sense for every edge ij, and the row sums and column sums for Pij essentially are marginal conditions. So this condition says you have to match the marginals or marginal distributions P and Q at both ends while designing this joint distribution Pij, and the objective function itself now can looks like essentially a expected cost under Pij. So this is an expected, this has the interpretation of an expected cost under the distribution Pij ranging over all I and all j of using a link or using a link or a route. Okay, so think of capital I comma capital J being drawn from the distribution Pij, and C of capital I comma capital J would be the random cost of using that link. This essentially lays down an expected cost objective. Okay, so by this, so one can also write this objective as the expected value of I comma j, capital I comma capital J being drawn from P of C, in this notation it's C capital I capital J. Okay, so the aim is to minimize, is to find a distribution Pij to try to minimize its expectation under a given cost structure, right. So how does in some sense one go about solving such optimal transportation cost problems? One solution is given by the principle of coupling from probability theory. So what is coupling here? Let's review this definition. So if you are given two probability spaces x, let's say calligraphic x with measure P and calligraphic Y with measure Q. If there are two probability spaces, then a coupling of P comma Q or a coupling of random variables with distributions P and Q is an appropriately constructed pair of random variables X and Y constructed on some probability space omega with some distribution with some having its own measure, let us say Pxy, such that its marginals satisfy X distributed according to P and Y distributed according to Q. Okay, so in short, if you are given two probability distributions P and Q, any construction of joint random variables X and Y whose marginals are respectively X distributed according to P and the Y marginal is Q is called a coupling of the measures P and Q or the distributions P and Q. So notation for this is that we say X comma Y is a coupling of P comma Q or Pxy is a coupling of these two distributions. The joint distribution Pxy is a coupling of the tuple of marginals P and Q. We will also find it very convenient to denote by calligraphic P. Okay, calligraphic P of P comma Q denotes the set of all possible couplings of P and Q. So this is an abstractly defined set, but anytime that you can define a probability space with a joint distribution for two random variables with the individual marginal distributions being P and Q, any such construction in some sense is assumed to belong to this calligraphic P comma Q. So by the way, it's easy to see that this calligraphic P of P comma Q is always non-empty. So one can in particular always construct the very trivial coupling between two measures P and Q, which is the product distribution of P and Q, so or the independent coupling. So you can just define on the probability space calligraphic X cross calligraphic Y the product measure Pxy, which is the product measure of P and Q, and that trivially satisfies the marginal of X or the distribution of X being P and the distribution of Y being Q. So this set of all couplings is certainly non-empty. We don't have to worry about the emptiness of it. Okay. So this is essentially the idea of coupling, and it's often used to great effect in many areas of applied probability and stochastic processes, and we'll actually be using it to understand the connection to transportation cost problems and ultimately to concentration of measure inequalities. Okay, so in particular there are also objects called deterministic couplings, which are just couplings with certain extra properties. So in particular a deterministic coupling T from X to Y is you can think of it in different ways. It is just essentially a change of variables from P to Q. Okay, so in our transportation cost problem, it essentially represents any transference plan that does not split material at source or destination. So every the amount of iron ore at every site I is uniquely destined to go to a certain other site J and so on. Okay, and vice versa. So this is just a change of variables from P to Q, or in other words, for all functions, for all nice enough functions phi, you have that the integral over y of phi y q dy is the same as the integral over x of phi of tx. T of x is essentially where x gets sent to in the y domain, integrated against the distribution P. So in our discrete iron ore example, as I said, a deterministic coupling T would be any function that maps the set of integers 1 through m to the set of integers 1 through n, such that for all I comma j, Pij equal to exactly Pi if j is equal to T of I. Okay, so that's what is called a deterministic coupling. It's a deterministic way of mapping any x to any y. Okay, so you do not split, you do not have multiple destinations for any of the sites or domain elements of x. Each domain element of x is assumed to send material or transport material only to a uniquely identified site in the y domain. So optimal coupling or optimal transport is the solution or minimizer for the what is called the Monge-Kantorowicz minimization problem. which is a very general problem defined in general probability spaces. So, if one is given two measures P and Q, CPQ is defined to be the minimum or more generally the infimum of the expected value of C of x comma y. So, if C is a given function on x cross y, which is the transportation cost function, then the Monge-Kantorovich minimization problem asks you to find the minimizer of expected value of Cxy over all possible joint distributions of x and y that respect the given marginals P and Q. Okay, so this is the optimal transportation cost problem. And there is an entire branch called optimal transportation theory that studies the existence and properties of solutions of the Monge-Kantorovich minimization problem. The minimization is over all joint distributions Pxy lying in the set of couplings of x and y. In fact, sorry, this is not q, but this is y, or pq, depending on the notation that you choose to adopt. And any such joint distribution or a coupling is called a transference plan, and those that attain the infimum are called optimum transference or optimal transport plans. So this is a fairly general and abstract problem that has been studied for a lot of time in analysis and probability. But let's look at some well-known special cases of the optimal transportation problem in terms of the cost structures C. Okay, so the first example that I'd like to present here is what is called the existence of a deterministic optimal transport plan or a Monge coupling. So recall, deterministic optimal transport plan is just a plan that sends material from every location I uniquely to a unique destination J. Okay, so in general, so we begin with a remark saying that in general, one cannot hope to find a deterministic coupling between two given marginals P and Q. So in general, a deterministic coupling or an optimal transport plan need not exist, need not even exist between given marginal distributions P and Q. So as a simple example, you can just take P. So let's just take the space as the set of space of all real numbers, and if you have P as a Dirac delta probability distribution supported on some point x, and Q as being a very nice absolutely continuous with respect to Lebesgue measure distribution, let us say a Gaussian measure on R, then there is clearly no optimal transport plan. There is no deterministic coupling that can basically send probability mass, all of which lies at x in the P side, to a unique location on the Q side, because Q insists that the probability mass must be spread all over the place across real numbers. So there is no way of mapping in a deterministic way sending material from P to Q. Okay, so that's what this statement says. So, however, with some appropriate regularity conditions, a Monge coupling actually can seem to exist. So, however, with some regularity conditions or smoothness conditions on the probability measures P and Q, a Monge coupling, which is essentially a deterministic transport plan from x to y, exists. So here is a set of regularity conditions as an example that makes this possible, and this is again a famous setting where we have a metric cost. So what do we mean by this? Let's suppose that the x and y domains are both, let's say, Rd. So if both of these are Rd, and P and Q are both given to be the marginals P and Q on RD are both given to be absolutely continuous measures with respect to Lebesgue measures. So there are two probability densities. Okay. So let's say P and Q are two given probability densities with the cost structure C x comma y between 2 points in RD just being the standard norm difference between x and y. This can be any norm, by the way, defined on RD. Then the optimal cost, the optimal transportation cost. So let's call this setting as P1. So the optimal transport cost for P1, which is which we defined as CPQ being the inf over x comma y in the set of all couplings of PQ of expected value of the norm difference between x and y. So in fact this turns out to be actually a measure of distance or a metric on the set of all probability distributions P and Q. So this can actually can be regarded as a distance measure or a metric between probability distributions P and Q. So the smaller this is, you can think of P and Q being more similar, and in fact this is also called by other names such as the earth mover distance, which is commonly used in computer science, or the alternative name is the Wasserstein distance in statistics. Okay. In fact, one gets this nice duality principle here where you can express CPQ as both a minimization problem and an and a maximization problem. So recall that we defined CPQ as the inf of the expected value of x minus y, the norm difference between x and minus y, where x comma y are coupled according to P comma Q. And it turns out that you can also write this in a dual way. It's the supremum over all, if the supremum over EQ hx minus EP hx over all functions h that are one Lipschitz continuous on RD with respect to the norm, whatever norm you take. So in fact this is what is called Kantorovich duality or Kantorovich Rubinstein duality. Okay, this has the following really nice form, which in some sense is connected to what we want to do with deriving concentration inequality. So this is the first time we are seeing the appearance of functions like the expected value of a certain random variable with respect to two different probability measures P and Q. And this is also called the, as we said, this is called the Wasserstein one distance between probability measures P and Q. Okay. So just a side note, the Kantorovich Rubinstein duality at the simplest level essentially says that the solution of a certain infimization problem can also be represented as a solution of certain supremization or maximization problem. And one of the simplest ways of seeing this is in the discrete setting. So, in the discrete setting, if we recall what our problem was, it was minimizing the total, it was a minimization of the following cost, which is linear over the variables Pij. Okay, so the objective function is linear over Pij's, and the constraints are also linear over the Pij's. Okay, so this is actually a nice linear program, the solution for CPQ or the optimal transportation cost in the discrete case. And as we know, you can always take, so every linear program has a dual linear program, and in fact interpreting the dual linear program appropriately is what gives you the Kantorovich-Monge duality result. So, it works to much greater generality than just the discrete case, and so we have results of this form. That if you define if you use a standard metric as the cost function in your two spaces, then the optimal transport cost turns out to be related to another dual problem, which essentially for whom the domain is the set of all Lipschitz functions between those two spaces. The second example, which is very well studied of transportation cost problems, is the one of the Hamming cost. So, let us consider the case where you want to transport from two given measures on the same space, that is script x equal to script y, and the cost function between x and y is just 1 if x is not equal to y and 0 otherwise. So, each time that you transport material, any amount of material from a site x to a site y which is not x, you end up paying a unit cost. You end up paying a unit one transportation cost of 1 per unit material. So, this is in fact another metric cost. Indicator x not equal to y is what is called the trivial metric over the space x, or the Hamming metric. Okay, so imagine that you have the spaces being the same, and you have two given distributions p and q on x, and you want to try to find the coupling between between p and q that minimizes the expected value of the indicator that x is not equal to y. So, the solution to this optimal transportation problem has been well studied and understood, and in fact can be can be seen by the following result that we will prove. This is called by various names, one of them being the maximal coupling lemma, which we will also use in the subsequent lecture. So, for the optimal transportation problem with the cost structure given by the Hamming distance or the Hamming metric over x cross y with y equal to x, we have that the solution, the optimal transportation cost, is nothing but the total variation distance between p and q, okay, which we will call dTV. So, dTV is the classic total variation distance measure, which is defined, which can be defined again in various ways. One of the most common ways to define it is the supremum over all possible subsets of the space, or between the of the difference between the probability of A as measured by P and the probability of A as measured by Q. Okay, so thanks to this lemma, we also know that CPQ, the total variation distance, has has the flavor of a minimization problem as well, because CPQ was defined to be the minimum over all P, which is a coupling of P and Q of the probability that, so expected value of the indicator that x is not equal to y. So, it is the probability that x is not equal to y over all joint distributions P with given marginals P and Q. So, the content of the lemma essentially says that the total variation distance is actually the solution of a transportation cost problem, where the cost structure is given by indicator x not equal to y, and in fact the name maximal coupling arises as we will see in the proof of the lemma, by actually explicitly constructing a coupling between P and Q that achieves the DTV, the total variation distance. Okay, so let's move on to the proof, which is a rather elegant proof. So for reasons of simplicity, we will only show the proof for discrete spaces X. The general case can be shown with some more technical effort. In fact, we can assume that X is finite just for the sake of simplicity. So so the first step is to say that for every possible coupling P of X and Y, or P and Q, the probability that X equal to Y is exactly the sum over all X in script X or calligraphic X of the probability that capital X equal to capital Y equal to small x. So it's basically the sum of probabilities of pairs that lie on the diagonal. Okay, so the set X comma X, so it's the probability of the set X comma X where X ranges in X, and this is called the diagonal. It's often called the diagonal in the joint for the joint probability distribution. And one can split this sum over X in all script X over X in any set A and the complement. So doing that gives rise to the inequality. So if you just take X running over A complement of this expression and drop the condition that Y has to be equal to X, you just get probability that X equal to X. And likewise the remainder of the sum is X lying in A of the probability that you insist that only Y be equal to X, and this holds for any subset A of X. Okay, and now by the definition of coupling, the the bold P of X equal to X is simply the regular P of A complement. P of A complement, the second term is by definition of the coupling, it's Q of A, and this is 1 minus PA minus QA. Okay, so P of X X being equal to Y is upper bounded by any such expression for all A in X, and in particular one can basically take the the subset A that gives you the tightest upper bound or the smallest upper bound, which is to say take the set A that essentially reaches the supremum in the definition of total variation distance, and so this implies that the probability that X equal to Y is at most 1 minus the total variation distance between P and Q. This is just the same as saying that probability that X not equal to Y is lower bounded by dTV of PQ. So this gives us one side of the result that we wanted. We essentially want to show that this holds with equality. So we obtained the greater than or equal to part. Okay, so this is just the same as saying CPQ. So for any such coupling, since there is a lower bound of dTVPQ, it means that CPQ is lower bounded by dTVPQ with the Hamming cost. So we want to essentially show the other direction as well, that CPQ is less than equal to dTVPQ. So for that we will actually construct an explicit coupling. So to show the other direction, that is the achievability, we will actually show CPQ equal to dTVPQ. Let's start by taking the subset A as the set of all elements X where P is larger than Q. P is at least Q. Okay, so it's easily seen that in this situation the total variation distance between P and Q is simply the size of A as measured by P minus the size of A as measured by Q. So, this gives us an expression for dTVPQ in terms of this distinguished set A. And now we will set about constructing a coupling that a joint distribution between P and Q, or between X and Y, whose X marginal is P and whose Y marginal is Q, and which essentially minimizes the probability that X and Y are different in the joint sense. So, for doing that, the operation is quite naturally is illustrated by drawing a figure. So, let me draw the following figure, where I'll draw a two-dimensional figure. So, let this square on the xy plane represent the Cartesian product of this is x. So, the x axis is the space x and the y axis is the space y, which is assumed to be equal to x, but think of it as y. And we can, so let us assume that we have arranged the elements of x and in the same order arranged it along y as well, such that the first block of elements represents the set A. Okay, so the set A where P is always larger than Q, and the remainder is A complement. So, imagine that the elements of X are arranged in order, in some order, such that the elements in A come first and then the elements in A complement come later. And you follow the same ordering along the y axis as well. So, so here lies A and here lies A complement. Okay, and imagine lining up all these elements, and then the square represents the Cartesian product of all pairs x comma y, where x belongs to script x and y belongs to script y. So, we have this diagonal here. Okay, so this diagonal is essentially the set of all x comma x, where x ranges over big script x. So, that is a diagonal in this space. Now, what we want to do, so really imagine there are only finitely many points in x on the x and y axis. So, this is a finite Cartesian product. So, it is a grid of finitely many points. So, what we want to intuitively do is to define for every grid point on this square a probability number p of x comma y, okay, such that two properties must hold. One is that the sum along all vertical lines must be equal to the vertical the horizontal distribution px, and the sum over all horizontal lines must be equal to the given numbers qy. Okay, so let me demarcate 4 important quadrants here. Okay, so these are 4 corners defined by the Cartesian products of A with A with A complement, A complement with A, and A complement with A complement. So, all we have to do is design a distribution on this entire plane. So, distribute probability mass across this entire square such that the projection of that probability mass on the x axis gives you the marginals px, and on the y axis gives you the marginals py. Now, what do we have to intuitively do to minimize the transportation cost? We have to try to keep x and y as equal as possible. Okay, so that intuitively translates to trying to put as much probability on the diagonals as we can. Okay, so think of it as if you are able to put as much probability on the diagonal as you can, then you have effectively minimized the chance that x and y are different or not lying on the diagonal. So, let us consider a point. So, let us consider a point x here on the diagonal or x comma x on the diagonal. Okay, so let us consider a point x comma x on the diagonal. So, so suppose we want to put the largest possible probability on this diagonal point x comma x such that the marginal constraints are met. what is the largest probability we can put? So on one hand, we know that if we sum along the vertical line which passes through x comma x, we must get px, and if we sum on the horizontal line that passes through x comma x, we must get qx finally. But we know that px is greater than or equal to qx. So the theoretical maximum probability that one can put at the point x comma x is limited by the smaller one out of px and qx, which in this case happens to be qx. So what we can do is we can put a probability mass of qx on each such diagonal point x comma x where x belongs to A. Okay, the moment we put such a probability qx on this diagonal point x comma x, the horizontal sum already has qx. So there can be no more probability on the vertical strip passing through x comma x at any other point apart from x comma x. So what it says is that it rules out, so by x's I mean that there can be no probability mass sitting at any of these points along this horizontal line. Okay, so x means that there is no or zero probability mass, because you have exhausted all the qx by placing it exactly at the diagonal point. So you cannot put any more probability mass along this vertical line passing through x comma x. Okay, and this essentially holds for, you can do this construction for every x in this set A and x comma x on the diagonal. So that effectively says that apart from this diagonal, there can be essentially no probability in this entire part. You cannot put probability mass anywhere here. By the same token, one can also consider points x comma x with x lying in A complement. Okay, so in fact let me call this point y comma y. Take a typical y comma y on the diagonal where y lies in A complement. So here py is strictly less than qy. So it follows that the largest amount of probability mass you can put here is py, and it also follows that by putting py you have already exhausted everything on this vertical strip. So you cannot put anything on this vertical, any more probability mass on all points on this vertical line apart from the diagonal. Okay, and so that essentially rules out, by generalizing this y along the entire, by sweeping y along A complement, that you cannot put probability mass anywhere here and anywhere here. Okay, so we managed to place probability mass on the diagonals by using the principle of largest possible probability on the diagonal. Okay, so okay, and so the only remaining mass, so there is of course remaining probability mass that we have to place on this figure, and it follows that we can only place it, the only space to place it is in this northwest quadrant of this figure, which is essentially over x comma y, such that x lies in A and y lies in A complement. Okay, so what do you have to satisfy here? Let's look at what are the operational constraints here. So the operational constraints here say that, take a typical point here which we will call x comma y. So the x coordinate is small x and the y coordinate is small y. What we must ensure is that if you imagine placing masses at every point in this, every grid point in this highlighted yellow square, then what it means is that along this vertical strip here in this northwest quadrant, the total mass, probability mass, must be the difference between what was left over, what you put on the diagonal, and what you totally wanted to put. So that is in fact the difference between px minus qx. So you had a total of px to put on the vertical diagonal, out of which you put qx on the diagonal, and so on the part apart from the diagonal there is a remainder of px minus qx that you have to put. And similarly along this this horizontal part, the total mass in the horizontal part must be qy minus py. So for every such horizontal and vertical line passing through x and y in the northwest quadrant. The distribution must be such that you should find px minus qx on the horizontal part and py minus qy as a total on the vertical line segment. Okay, so this is in fact now just it's like a product constraint. So the simplest way of achieving this is just by putting let us say at each point x comma y. So for x and y belonging to A cross A complement, that is the northwest quadrant, perhaps we can put a mass which is proportional to what we want there, okay, proportional to the product of what we want there. We want px minus qx on the vertical segment passing through it and qy minus py on the horizontal segment passing through it, and we have to multiply by some constant here, okay, beta, that we will find soon. So if you put this kind of probability distribution, so take the total mass that you have remaining for the northwest quadrant and put masses at each xy following this product rule with an appropriate constant beta such that the total mass is exactly takes care of the remaining mass from earlier from after putting on the diagonal points. So what that means is if we sum over all y in A complement of beta, so let's sum the total vertical, let's try to find the total vertical mass here. So that's just summing over y in A complement, beta into px minus qx and qy minus py. What this gives you is beta into px minus qx comes out and you have y in A complement qy minus py, and by definition this is exactly beta into px minus qx into the total variation distance between p and q. Okay, so in order that this should equal px minus qx, so you can just take beta as 1 over the total variation distance between p and q, and that essentially fixes everything beautifully. So this was just motivation, this was sort of the natural way of trying to distribute mass to intuitively minimize the amount of probability mass, joint probability mass away off the diagonal, and in fact we can make this formal by saying that we can construct, what all of this has resulted in is the statement that we can construct an optimal coupling or a maximal coupling Notice that there can be several different optimal couplings. This is just one example that we have argued intuitively that can be constructed. So let's call this P star, which we will show is a coupling of P comma Q as follows. So we are now just going to mathematically and precisely define what we just, the procedure that we outlined for putting mass in this 2D plane on this 2D square. So for all x comma y, which are pairs in this square, a Cartesian product of x with x, define P star, the mass sitting at x comma y as follows. So if x is equal to y, if it's a diagonal point, then you just put probability, the largest possible probability mass there, which is min of px comma qy, if x equal to y, by our intuition. If you're not on the diagonal but you're in the northwest quadrant, then you put a probability mass of px minus qx into qy minus py divided by, so into beta, which is 1 over the total variation distance between p and q, if x is in A and y is in A complement, and everywhere else you don't put any probability, 0 otherwise. Okay, so this essentially defines a complete probability distribution where no probability mass is wasted over the entire 2D plane, over the entire 2D domain, which is the Cartesian product of x and x, as we just outlined or argued intuitively. And with this formal definition, I mean, this is almost true by how we constructed it, but you can mathematically verify the following claims that the right marginal properties are met. So P star of the set A, the entire of any subset A with the entire X just gives you the marginal over A, and P star measured over the rectangle given by the entire space X in the first coordinate and any subset A in the second coordinate gives you Q of A. This is following our construction. It's almost immediate by what we argued in the geometric figure. And more importantly, you can also check that P star X equal to Y using this definition above of this coupling is exactly so this is exactly the sum of all masses on the diagonal, which we argued that every x comma x you put the minimum of px and qx, and this is easily seen to be 1 minus dtv of pq. So equality holds here with the total variation distance, and so this is exactly one such coupling that achieves equality and proves this lemma. Okay, so just so that you don't get confused, the underlying idea here, which is what we drew on the figure, is to put as much probability mass on the diagonal as possible, and this naturally forces you to redistribute the remaining probability mass in the northwest corner. Redistribute or distribute or put the remaining mass or the remainder of the probability mass in the northwest corner or quadrant. Okay, so that's the construction of a maximal coupling, and you can also see that in general this maximal coupling that we constructed is not a deterministic coupling. In general, namely because for a point x in A, the px probability actually was being spread out over this entire vertical strip, and that is why it's not in general a deterministic coupling. Right. So we now return to the relationship between transportation cost inequalities, and we'll move towards the relationship with the concentration of measure bounds. So we'll just conclude this lecture right now by saying that a transportation cost inequality. So in general, what is called a transportation cost inequality is simply an upper bound for the optimal transportation cost CPQ. It's just an upper bound for CPQ. Okay, so a famous example of such an upper bound for CPQ is again for this Hamming distance. So for CXY, the cost structure given by the Hamming metric or the trivial metric between x and y on x cross x. We already know that the optimal transportation cost with this cost structure is the total variation distance between P and Q, and one upper bound on dTV is what is given by Pinsker's inequality, which is 2 times the KL divergence between P and Q. So this is called in information theory as Pinsker's inequality, which we will see and prove in the next lecture. So this concludes this lecture. A very nice reference, if you are interested, for reading up about optimal transportation is the following. So for transportation theory, so you can read the lecture notes by Cedric Villani on optimal transport, old and new. These are lecture notes. These are series of lecture notes from 2006. And of course, you can always refer to the chapter on transportation, the transportation method chapter in the book that we are following, which is the Concentration Inequalities book by Boucheron et al. Thank you.